Ever wondered how a computer can go head-to-head with a grandmaster in chess and actually win? It seems like it's thinking dozens of moves ahead. Well, it's not just about throwing massive amounts of computing power at the problem. It's about something much, much cleverer. It's about teaching a machine how to think strategically. And today, we're going to break down the logic that teaches machines not just how to play, but how to win.
So let's just start with the big question right up front. How do you teach a machine to win? And I don't just mean solving a puzzle. I mean winning a game where you've got an opponent, another intelligent player whose only goal is to make you lose. That's where things get really, really interesting.
Okay, to really get a handle on this, think about the difference between a puzzle and a game. On one hand, you've got something like a maze, right? There's a start, there's an end, and the maze itself doesn't change. But a game like chess, whoa, that's a completely different animal. The board is always changing, and your goals are in direct opposition to your opponent's. You can't just find one solution. You need a strategy that reacts and adapts to what your enemy is doing.
Right. So, to crack this problem of thinking against an enemy, AI experts came up with a special set of techniques. And this is what we call the world of adversarial search.
So, what exactly is adversarial search? Well, at its core, it's a way for an AI to make the best possible decision when it knows someone else is actively trying to mess up its plans. The whole idea is to look ahead and anticipate what your opponent is going to do. It's not about finding your best move in a perfect world. It's about finding your best move assuming your opponent is also about to make their best move. Now, the kinds of games we're usually talking about here are what we call zero-sum games. This is a super important concept. It just means that for me to gain something, you have to lose that exact same amount. There's no everybody wins scenario. My win is your loss, and your win is my loss. That simple, brutal logic is what powers the whole system.
And that leads us right to the first big, famous algorithm for this stuff. It's called minimax. It's this really elegant, logical method that lets an AI predict what an opponent's going to do, and because of that, figure out its own best path to victory.
To really get minimax, you have to imagine two competing forces. First, you've got Max, the maximizer. That's our AI. Its job is simple. Make moves that lead to the highest score possible. And playing against it is Min, the minimizer. That's the opponent. Min's job is to do everything it can to force the lowest possible score for Max. It's this constant tug of war. The way Minimax works is actually pretty cool. First, the AI imagines a giant tree of every single possible move. Then, it goes all the way to the end of each branch and gives it a score. Like +10 for a win, -10 for a loss, maybe 0 for a draw. But here's the magic trick. It starts working its way backwards from the end. At each step, it assumes Min will pick the lowest score and Max will pick the highest. This whole process lets the AI see which first move leads to the best possible outcome it can guarantee, no matter what the opponent does. Let's make this way less abstract. Imagine the AI looks a few moves ahead and sees 4 possible ways the game could end. From our AI's point of view, let's say these end states have scores of 3, 5, 2, and 9. Think of these as the final scores on the board. These are the leaves of our game tree, and we're going to work our way back up from here.
Okay, so let's back up one level. Now it's the opponent's turn. It's Min's move. On one side, Min has a choice. Let the game end with a score of 3 for us or a score of 5. Since Min wants to minimize our score, it's obviously going to choose the path that leads to 3. On the other side, Min is choosing between a 2 and a 9. Easy choice for the opponent, right? It picks the path that sticks us with the 2. So, now we're all the way back at the beginning. It's our AI's turn, and it has to make a decision. It knows with perfect certainty that if it goes down path 1, the opponent will force a final score of 3. And if it goes down path 2, the opponent will force a final score of 2. So, what does Max do? It's a no-brainer. To maximize its score, it chooses the first path, which guarantees an outcome of at least 3. And that right there is the minimax decision. Now, minimax sounds perfect, right? It's logical, it's guaranteed, but there's one tiny problem. In any game that's even a little bit complex, trying to think about every single possibility is just,
impossible.
Just look at this number. For a game like chess, the number of possible sequences of moves is something like 35 to the power of 100. I mean, that's not just big. That number is ridiculously, mind-bendingly huge. It's bigger than the estimated number of atoms in the entire observable universe. No computer that exists or will ever exist can search a tree that big. It's just not going to happen.
And the experts put it pretty bluntly. As one source says, the problem with Minimax search is that the number of game states it has to examine is exponential in the depth of the tree. Basically, for every extra move you try to look ahead, the amount of work multiplies like crazy. It just gets out of control, fast. We need a smarter way to search, not just a harder one.
So, what's the big idea? What's the clever solution? Well, what if the AI could figure out that an entire branch of the future was a total dead end, without even having to look at all the moves down that path? What if it could just know? This is the brilliant insight that makes all of this practical.
This amazing trick works by keeping track of just two little values. The first one is called alpha. You can think of alpha as the best score that our AI, the maximizer, is already guaranteed. It's like a high watermark. It's the floor for our score on any given path. We know we can get at least this much.
And the second value, as you might guess, is beta. Beta is the flip side. It's the best, meaning the lowest score that the opponent, the minimizer, can force on us. So if alpha is our guaranteed floor, beta is the ceiling that the opponent is trying to impose. And it's the relationship between this floor and the ceiling that creates the magic. And this all leads to one simple but incredibly powerful rule. It's called pruning. You stop searching down a branch the very second that alpha becomes greater than or equal to beta. Think about it. Why would you keep exploring a path where the best the opponent can do to you, beta, is already worse than a score you're already guaranteed somewhere else, alpha? You wouldn't. You can just snip that entire branch off the tree and ignore it.
Let's see this in action. It's actually pretty intuitive. So imagine our AI has already checked out one part of the game and found a line of play that guarantees it a score of at least 15. So its alpha, its floor, is 15. Now it starts exploring a brand new branch. And down this new path, it sees the opponent can make a move that would result in a score of 10. Boom! The AI stops right there. It knows the opponent, being a minimizer, will always force an outcome of 10 or less. So why would our AI ever explore this path further, a path that leads to a maximum score of 10, when it already has another option that guarantees 15? It wouldn't. The entire branch is pruned, gone. That's alpha-beta pruning, and it saves an unbelievable amount of work.
Okay, so this is all super cool for teaching a computer to play tic-tac-toe or chess. But this kind of strategic thinking, it's not just for games. These ideas have applications that stretch way, way beyond the board.
I mean, you have the famous game-playing AIs like Deep Blue and AlphaGo, of course. But the same logic is used to create the AI enemies you fight against in your favorite video games. But it goes further. This stuff is used in military simulations for wargaming different strategies, in economic models to try and predict what competitors in a market will do, and even in automated high-speed auction systems. Basically, any situation where you have competing agents with conflicting goals can be modeled as a game. So, we figured out how to build a machine that can master strategy, that can anticipate every logical move we make. And that leaves us with a pretty deep question to think about. If a machine can achieve strategic perfection by being purely logical, what does that tell us about our own decision-making and all the biases and blind spots we have as humans?